Welcome to SPT online classes. Today we are going to discuss some surprising facts about radioactive decay. We know radioactive decay are of different types. One is alpha decay, correct? The other one is beta decay. Beta decay itself are of two types, beta plus decay and beta minus decay. We have gamma decay also. So you might be thinking, what is that so much to get surprised in this decay? What else is there something new in this decay to know about it? Anyways, few of my students asked me that in beta plus decay process, okay, you might have studied the reaction of that. In beta plus decay process, you might have seen that a proton is converting to a neutron. If you do remember this particular reaction, a positron and a neutrino. In a beta minus decay, we know that a neutron is getting converted to a proton and an electron and antineutrino. So what's so much to get surprised in this? But if you have clearly observed these two reactions, you might have seen something special, that a neutron can get converted to a proton. But my question is, how can a lesser mass particle proton gets converted to a higher mass particle neutron? How many of you have noticed this? Proton is having mass less than neutron. Then how come neutron, positron, neutrino can all come from a proton particle? This is my question. This is the question posted by many students. So let me tell you. An isolated proton, okay? Isolated proton means a proton which you are taking it as like independent, separately from the nucleus. Imagine if you have a proton with you. This will never get converted to a neutron, a positron and a neutrino. This will never happen if you are taking an isolated proton. So when will this conversion happen? This can happen only in an unstabilized nucleus. Which one? The proton conversion to neutron. That can happen only in an unstabilized, let me write here, unstabilized nucleus. So a confusion will be there. Then how come a lesser mass particle gets converted to higher mass particle? The answer for that is because of the help of the remaining protons in that nucleus. If you take nucleons, say nucleons consist of protons and neutron, and if one proton is getting converted to neutron, it is not because of the ability of that single proton, it is because of the team effort of all other protons, or we call it nucleons, protons and neutrons. Got it? So it is because of that team effort that that is helping the proton to get converted to the neutron and positron and neutrino. Understood? Now something like this you might have seen in the concept of binding energy. Let's refresh that part. Binding energy. Imagine there is a proton and an electron at infinity. You are bringing these two to form a hydrogen atom. hydrogen atom definitely contains a proton surrounded with an electron. What will happen? You're trying to fuse it, correct? During fusion, some energy is released. Some energy, let me write it as energy. Now, what will happen if you give some energy to a well-stable hydrogen atom in order to split it into proton and an electron? How much energy is actually required to happen this process? The same amount of energy which is released in the fusion process. We call that energy as the binding energy. So binding energy is the energy which is used to split a well-stable hydrogen atom into proton and electron. It is that energy that which is bringing all these subatomic particles together. It is that energy which is being released out when you bring these nucleons together. Understood? So binding energy is coming due to the mass defect. What is mass defect? So if you take the mass of a proton and if you take the mass of the neutron, you add it together. Okay, if you take okay, fine. If you take the mass of the proton and if you take mass of the neutron, you add it together, it will be greater than the mass of the nucleus which is formed. Let me write it as X, which is having an atomic number Z and mass number A. Okay, so imagine there are some Z number of protons and A minus Z number of neutrons. So the mass will be definitely greater for the separate particles or individual particles. It will be greater than the mass of the nucleus which is formed. So what is the reason for that? It is because of a defect. We call it mass defect, the difference in the mass. This mass defect times the square of the velocity is what we call as binding energy. Got it? Binding energy. We call it binding energy. So binding energy. Fine. So here also what you are seeing is that you are expecting that the mass will be conserved, but no, it's not happening. There is a difference in the mass between the reactant particles and the product particle. There is a difference in the mass, and some mass is actually getting reduced, and that reduced mass, what we call as mass defect, is getting converted to binding energy. So the initial question was that how come a proton gets converted to neutron? So that is why I mentioned about binding energy also, because here also you can see that mass differences. Now something else I need to add up to this is that you know about alpha decay, which I'm not going to explain. What is alpha decay? Alpha decay is when a element of mass number greater than some 204 it will get decayed by releasing an alpha particle. Okay, alpha particle means what? A particle which is having 2 protons and 2 neutrons. That is what an alpha particle it is. So once an alpha particle is released, then the daughter nuclei will be reduced. That means, let me write over here, XZA. When an alpha particle is released, it will become a daughter nucleus of atomic number Z minus 2 and mass number A minus 4. There is nothing surprising element in an alpha decay, but there is something else. One more decay is there. We have just mentioned about beta plus beta minus decay. In beta plus decay, I just mentioned about the surprising conversion of proton to neutron, which is really unexpected. And understand one thing, that beta plus decay is not so common. There is one more decay which is what we studied as gamma decay. Let's discuss about gamma decay. What is something special in that? When will gamma decay happen? Gamma decay will happen if you take a mother nucleus, say X, And because of some alpha decay or beta decay or gamma decay or a series of decays, there will be a recoiling effect for this mother nucleus. Remember, this mother nucleus will turn into daughter nucleus, say Y. Understood that much? Now this is an unstable daughter nucleus. Because of the recoiling effect, it is very unstable and it will try to come back to its normal original ground state. During this process, it will release some energy in the form of light or photon. We call it gamma decay. So gamma decay will happen when nucleus jump from higher orbit states to lower orbit state because of its instability. There is something else which is what we call as an electron capture process. Have you heard about that? Electron capture process. Electron capture process. This might be something new for you, but still I'm just telling it. Electron capture process means sometimes the nucleus, okay, this nucleus is very hungry, imagine. It might sometimes capture an electron, okay, a surrounding electron. What will happen? The proton inside the nucleus combines with the electron to form a neutron and a neutrino. Okay. Now, when will that happen? Once it happens, remember, the mother nucleus, say X with proton, atomic number Z and mass number A, when it combines with an electron, what will happen? It will form to a daughter nucleus of, say, Y, atomic number Z minus 1, mass number remaining same, plus neutron, plus neutrino. Anyways, neutron I don't need to add, fine, neutrino. This is conserved in charge, but it is not conserved in mass. If you just check, the mass or the energy is not conserved. And that difference is what we call as Q value. Q value is not a term that you can use here only, but you can use it in any nuclear process. You can use the Q value. What is Q value? It is the difference in the energy between the reactants and the products. Got it? The reactants will be having definitely higher energy compared to the energy of the products. And that difference is what we call as Q value. So why I'm mentioning this? The reason is because once an electron is caught by a nucleus, once it falls into the trap, there will be a vacancy. Into that vacancy, our electron at higher orbit will jump because it always wants to fill the lower orbits. What will happen during this process? During this process, once again, a photon is emitted. That photon, that light, we call it X-ray. So this is how an X-ray is used to come. So X-rays come during such processes. Understood? So we studied about alpha decay, beta plus minus decays, gamma decay, X-ray. Now, where can you include all these things? In the spectrum. Which spectrum? Electromagnetic spectrum. Electromagnetic spectrum. Now, there is a lot of confusion happening in electromagnetic spectrum order. Let me make it clear. There are different methods you can study, by different shortcuts you can study, but in some shortcuts I came to know that there are some confusions coming or misleading information is getting into it. Let me make it clear. We have radio waves at the top of the list, then microwaves, then we have infrared, correct? Then we have visible spectrum, then we have UV, which is ultraviolet, we have X-ray, we have gamma rays. there is no alpha ray and there is no beta ray in this list. Make it very clear, because alpha and beta, they are not photons. If it is photon only, we have to bring it into the list. So alpha particles and beta particles are not there in the list. That's the first point. Second point is that many of you might be maybe knowing that this visible light, okay, this visible spectrum, this is the only light. They might be studying like this, that this is the only part of the light. No, it's not like that. The entire spectrum is what we call as light. Everything is light. Radio, micro, infrared, UV, X-ray, gamma, all radiations are basically light. They are photons or packets of energy. Don't get confused that visible part is the only light. And you might be studying like radio, micro, infrared, light, UV, X-ray, gamma. No, don't study like that. You have to study as the entire spectrum or each of these things under the category of light. When I say so, let me make a small point that radio waves, they have got a slight speciality, but that is not in part of the syllabus. But still, radio waves, there are so many people defending it and against it, treating it as light. So many are saying that it is light, so many are saying it's not light. Whatever. From an NCERT point of view, let's consider it as light itself. Fine. So we have X-rays and gamma rays in the bottom list with very high frequencies. Understand? So today we studied three things basically. That a proton can get converted to a neutron, a positron, and a neutrino during an unstable nuclear decay process. It will not get converted if it is an isolated proton. That is in the case of a beta plus decay. In the binding energy concept, what did we study? The mass of the reactants will be greater than the mass of the sum of the masses of reactants. I should say like that. The sum of masses of reactants is greater than the sum of masses of product. The mass is not getting conserved there. What happens to the difference? We call it that mass as mass defect, which is getting converted to energy. So energy is getting conserved there. What is the reason? The reason is because as you go to subatomic particles, the wave concept is dominating and the mass concept is, or the particle nature is going down. Wave concept is going up. So as you go below, you have to give more importance, priority to energy concepts rather than mass concepts. Understood? Then we studied something else, which is the electron capture concept. Electron capture concept. And that is how X-rays are formed, right? Electrons are getting captured by nucleus, and because into the vacancy, electrons from higher orbit are filling that vacancy by releasing photons called as X-rays. And with a last point, which can be highly contradictory for all of you, let me conclude this by telling one point. Microwaves. Here we have microwaves. And this is the microwaves are the main reason for the communication of mobile phones. I have said this in many classes. And there is a big doubt that whether microwaves can cause many issues to human cells. So let me make it very clear that microwaves have got frequency lesser than visible waves. You can see it in the list itself. You can see that microwave is having lesser frequency than visible spectrum. So if you are In any case, if you are getting some diseases, says due to, say, some people say that because of microwaves can cause cancer and many other things. So if people are not getting diseases due to visible spectrum, which is of higher frequency range, how will they get these kind of diseases due to microwave spectrum? Just think about it. So my point is, lower frequency radiations cannot cause issues. Issues can be caused only due to higher frequency, which includes UV, X-rays and gammas. Got it? Radio wave and microwave can't even make any. It can make influence on very smaller organisms. So there might be papers published with saying that these animals have got cancer cells, tumor cells are being growing because they are got radiated with microwaves. But nothing like that has been even now published in a proper journal with a proper relevance, saying that microwaves or radio waves can cause damage to human cells. Got it? Even though they can cause, or even though they can damage one or two cells, it's not going to make a big issue, something like cancer. Got it? So with that point, let me conclude today's topic. Thank you for listening.